In this section, you're analyzing functions for intervals of continuity or points of discontinuity. This section is about continuity of functions. Continuity is an important trait of functions in calculus because many of our theorems in calculus demand that our functions be continuous before we can use them. So the continuity test has three parts. A function it's a test at a particular x coordinates. So f is continuous at x equals c if and only if, and these three things have to be true. The function has to exist. The limit as x approaches c of f of x has to exist, and those two things also have to match. The reason that these things are broken out like this is because it goes from easiest to examine to most difficult to examine. So it's easiest to see whether your function exists. It's next easiest to see if the limit exists, and then the last thing you want to do is just check to see if those two things are equal. So the first thing I want you to do is think about a graph and try to sketch one that for which the continuity test fails, even though the first two parts pass. So take a minute, pause the video, and try to sketch a graph that fits these traits, and then come back when you think you've got an answer. All right, so my graph would, what I notice is just that f of 2 has to exist, so I definitely need to have a value there. So at 2, I'm going to have a value of my function. And the limit also has to exist, but it doesn't have to be the same as that. So the limit might be here. So I might have a function that gets close to that value there. So there's a hole for sure. And then there's a value somewhere else. It's not continuous because these two things are not equal. So it's failing that third bullet. All right, so for piecewise functions, we might want to test to see if the function is continuous where the two pieces of the function join together. So at x equals 1, if I want to test to see if this function is continuous, the first thing I should do is look for, does f of 1 exist? Well, f is defined at x equals 1, so f of 1 is defined as 5 times 1 plus 3. So f of 1 exists, and it's equal to 8. Next thing we want to do is check to see if the limit as x approaches 1 exists, and since it's a piecewise function, I'm going to want to check to see if the limit as x approaches 1 from the negative direction is equal to the limit as x approaches 1 from the positive direction, because that's the only way for that limit to exist. So I need to check both of those two limits to see if they match. So as x approaches 1 from the negative direction, I would use this middle part of the definition, because those are, oh, nope, I wouldn't. I would use the bottom part of the definition, because that's where numbers are smaller than 1. So I would use the bottom part of the definition, and we've already used that part of the definition, so we know that that's 8. And then this middle part is where the x coordinates are slightly bigger than 1. So that would be 1 squared minus 6. So it would be negative 5. Since these two values don't match, we now know we don't even have to go any further because this part of the test fails. So f is not continuous at x equals 1. I could ask you if the function is continuous at x equals 5. At x equals 5, there is no part of the definition that I would use. So f of 5 does not exist. This fails the continuity test even before I get started, really. F of 5 does not exist, so we're done with the test. You might, if you were an overachiever, you might notice that this part is okay. This part does pass, but since we've already failed the test, we don't need to go any further. I'll leave that to you as an exercise if you want to prove to yourself that the limit as x approaches 5 does exist. It's just that It can't be continuous already. I wanted to show you that it is possible for a function to be continuous since both of the two values I pulled out were not continuous. So is this particular function continuous at x equals 3? Well, f of 3 exists. For f of 3, I would use the middle part of the definition. So f of 3 would equal 3 squared minus 6. So it would be 9 minus 6, which is 3. So f of 3 certainly exists. It is 3. And the limit as x approaches 3, I would again use the middle part of the definition, but I can just do substitution. So the limit as x approaches 3 of f of x is going to be 3 as well. And so because those two match, yes, the function is continuous at x equals 3. There are 4 ways that a function can be discontinuous, and the two main ways are removable or non-removable. A removable discontinuity means that the limit exists, but the function does not match. Either the first part of the continuity test or the last part fails. But for removable discontinuity, that's the only one. For a non-removable discontinuity, there are 3 different types of non-removable discontinuities. Jump discontinuity means that my limits from one direction are not matching the limits from the other direction. So the limit as x approaches a from the positive direction of f of x is not going to match the limit as x approaches a from the negative direction. So that means that you would have a jump discontinuity. An infinite discontinuity means that you have a limit that is infinity, either positive or negative infinity. We also sometimes call this a vertical asymptote. And then a rare, but we need to mention it, there's oscillating discontinuity. Oscillating discontinuity means that you've tried to take sine or cosine of infinity, and it fails to exist. So an example is sine of 1 over x, because if as x approaches 0, so at x equals 0, 1 over x is infinity, you try to take sine of that, and your function just fails. So I have examples of all 3 types of discontinuities. So if I look at this example, where is it discontinuous and what type do we have? So the first thing I'd want to do in order to find that is I'd want to factor out my function as much as I can. So I have x plus 2 times x minus 2 in my numerator, and then in my denominator it looks like it's x minus 3 times x minus 2. So what I notice is that I had my x minus 2's did cancel, so x equals 2 is a removable discontinuity. It's removable because the limit exists. The limit is 4, but the function doesn't have a value at x equals 2 because there's a hole. Dividing x equals 2 would cause us to divide by 0. So f of 2 doesn't exist. It's removable. And then the other discontinuity we have is x equals 3. X equals 3 is a vertical asymptote. So this is an infinite discontinuity because that doesn't factor out. That 0 in the denominator doesn't factor out. Okay, this is a piecewise function. X squared minus 1 is just a parabola, so that's continuous. 2x is a straight line, so that's continuous. But if I look at the 2 pieces where they join up, I would want to look at what is the limit as x approaches 0 from the negative direction. And if I'm approaching 0 from the negative direction, I'd use the top part of the definition. So I'd have 0 squared minus 1, which would be negative 1. And then I'd want to take the limit as x approaches 0 from the positive direction. And so I'd use the top part of the definition. And so that would be 2x, or 2 times 0, which would be 0. Since those 2 limits don't match, that's called a jump discontinuity. So we have a jump discontinuity at x equals 0. And then the last one I already talked about. At x equals 0, you're dividing by 0, which isn't allowed, but then you're taking the sign of it, and that's called an oscillating discontinuity. Oscillating discontinuities are not going to come up a whole lot in this course. I just need to mention it because it's the last type of discontinuity. Having the definition of continuity allows us to have our very first calculus theorem. This is called the intermediate value theorem, and it states, if f of x is continuous on a closed interval, then your function takes on every value between f of a and f of b. I really want to point out that in order to use this theorem, you have to make sure you have a continuous function. And I'll give you a minute to think about it. Once you've thought about it, come back and we'll see a visual of this theorem. Okay, so here's a function that's continuous on the interval from a to b, and it's got this value at f of a, it's got this value at f of b, and it takes on every single y-coordinate between f of a and f of b. And you can see that it does, because this piece of the graph does take on that, all of the values from f of a to f of b. It takes on more than just those values, but the theorem just guarantees that your function will take on all of the values from f of a to f of b. I think when you see the visual, it seems like, well, why do we even need a theorem for that? The reason we need a theorem is it's actually very useful. Calculators use this theorem all the time when they're trying to find zeros of a function. They say, well, I noticed that the function is negative here and it's positive here, and as long as the function is continuous, then there must be a zero in between those two places. So here's an application of the intermediate value theorem. On which interval does this equation have a solution? So really we're saying this is continuous because it's just a cubic. So it must, if it is equal to 0, then what we'd want to do is check to see where is it negative and where is it positive. So if I plug negative 5 into this function, we get negative 125 plus positive 25 plus 1. And that's a negative value because negative 125. And then if I plug negative 3 into this function, I get negative 27 plus positive 9 plus 1. Well, that's also negative. So I don't have any guarantee that there'll be a 0 in between those two values. I'm going to leave the rest up to you, but it's not A because both of those two, like finding f of negative 5 and f of negative 3, those are both negative, so I'm not guaranteeing that there's a 0 between those. But one of these will give you a negative value and a positive value for the endpoint, so you know that it has to take on every value between a negative value and a positive value, so it would have to take on a 0. So here's our summary. Vertical asymptotes are points of infinite discontinuity. The limit doesn't exist. It's in some kind of infinity. A 0 in the denominator might be a vertical asymptote, or it might be a hole, so you want to factor those to see if you've got an asymptote or a hole. Piecewise functions can have jump or removable discontinuities. Removable means that the limit exists, and you can fill in the hole by reassigning the function, the value of the function there. A jump discontinuity means that the one-sided limits don't match, and you can't just fill in a hole to fix it. Oscillating discontinuities are rare, but it means that you've tried to take the sine of, or cosine of infinity.